Today's lesson is going to look at an application of vectors, which is relative velocity. I'm sure that we've all been involved in a scenario where you could see something moving, like a person, for instance, sitting beside you in a car. You're both moving at, say, 60 miles per hour inside the car, but as you look at each other, you don't appear to be moving at all. So we would say that if we have two people sitting inside of a car, person A and person B, the velocity of person A as measured by the person B inside the car would be 0. However, both their velocities as measured by someone standing outside would be measured at whatever the speed of the car was, which would be probably 60 miles per hour, let's say. So we're going to look at how vector addition can be used to help us solve these types of problems. So whenever we're considering relative velocity, we have to consider something known as the frame of reference. A frame of reference is a coordinate system for specifying the precise location of objects in space. So we would say, for instance, if we have the car moving down a street and we have people in the car sitting, we could say that our reference frame could be the motion of the car relative to the street or relative to the earth, or we could say that we have a person in the car, the velocity of the person in the car relative to another person within the car. So the two passengers could be relative to one another. So what we have is a scenario that if you're observing the velocity of the person in the car from inside the car versus outside the car, you're going to have different measurements in terms of their displacements, their velocities, their accelerations. A good example of that, let's suppose you're riding on a school bus and you toss you've got a tennis ball in your hand and you're tossing the ball up and down. And maybe someone sitting beside you looking at the pathway of the ball. Well, to the person sitting beside you, it could be that the ball looks like it's doing the following. It's rising and then falling, and it's all in one line. So we have velocity up, velocity down. But if you've got someone standing outside the bus while you're doing this and you're tossing the ball in such a way that they can see it, let's say the bus is moving in this direction, then it's going to appear that the ball is moving more in this pathway, more of a parabolic pathway rather than a straight line pathway up and down. So you can get very different observations from different reference frames. So let's take an example of how we can solve this type of problem. We're going to start with a two-dimensional problem where we're just looking at the two objects moving in the same direction, sort of like we did when we were doing vector addition. So we've got a person on a bus is observed by a seated passenger walking at 3.6 kilometers per hour from the back of the bus to the front of the bus. The bus is traveling at 85 kilometers per hour. What would be the velocity of the passenger walking as measured by a person who is standing on the side of the road? And so let's imagine that we have, first of all, bus velocity. Let's consider that to be positive. So we've got the bus moving in this direction. That means the person is going to be moving in the same direction because they're going from the back to the front of the bus. So we have some reference systems. And go back here, we have our frames of reference. So we're going to look at a way of using the frame of reference and notation to help us keep track of what we're doing in the problem. So let's call, first of all, we have a person on a bus is observed by a seated passenger walking at 3.6 kilometers per hour. So let's call that velocity the velocity of the person relative to the bus. And that's 3.6 kilometers per hour. And let's suppose we have also the bus is traveling at 85 kilometers per hour. So we could say that that's the velocity of the bus, which is normally a moving automobile is usually referenced to the earth. So we'll say bus to earth, and that's 85 kilometers per hour. Okay, so we're interested in what is the velocity of the walking passenger. The velocity of passenger relative to a person standing by the side of the road, which they would be standing on the earth. All right, so we can set this up so that we know, for instance, we have velocity of person relative to earth. And this is the object is moving, and this is the reference frame. We can set up our addition in such a way that we end up with, well, first of all, we're going to start with our person. So we're going to say velocity of person relative to bus. And we want to end with earth. And that would be bus relative to earth. So when we do this, if we do this, what this is going to allow us to do in the vector addition is convert between the start point and the end point in these. We're going to, our bus is the common factor, so we're sort of canceling that. And we're going to say that our velocity of the person relative to the earth is going to be our end result. Now we can also look at this from the standpoint of vectors. And so we have a velocity of our person relative to bus. Let's reverse that and put that in terms of an arrow. Person relative to bus, and that's 3.6. I should shorten that, because the other one is so much longer. Okay, and then we can say that we've got our other vector is going to be the bus relative to the earth. Alright, so let's, and this obviously isn't the scale, it's something large enough I can handle, but I can still shorten this a little bit. And let's put this in as velocity of person to bus, and this is 3.6 kilometers per hour. And this is velocity of, this is bus to earth, which is 85 kilometers per hour. And if we connect these, tip to tail, then what we're going to end up with is the velocity of this sum, the resultant, equals the velocity of the bus, the person relative to the earth, which is going to be, since they're in the same dimension, it's a simple addition, that's going to be our 3.6 kilometers per hour plus our bus to earth was 85 kilometers per hour. So that's going to give 88.6 kilometers per hour. And that sort of makes sense if you're thinking about it. So a lot of you probably had that number in mind before we ever looked at it. But the key here is I want to take a simple example and let you realize that if you set these up, I need person to earth, so I'm going to start with the one that begins with person, and I'm going to end with the one that ends with earth. And as long as I've got these two, one is a reference system and one is the object, I can cancel those, and I end up with leftover person to earth. So that's the way we handle the notation system. That will help in the vector addition. You also need to be able to look at it from the standpoint of actually just connecting the vectors. Let's go to another example. We have two cars moving in opposite directions. Make sure I've got my slides correct here. We have two cars moving in opposite directions on a highway. Car A, and let's call this car velocity of A relative to Earth is equal to 85 kilometers per hour. And that's to the east. Then we have car B, velocity of B to Earth is equal to 95 kilometers per hour to the west. So this is, of course, a negative 95 kilometers per hour. What's the velocity of B relative to A? Okay, so let's sketch some vectors first. We've got velocity of A relative to Earth, call that 85 kilometers per hour, and we've got B relative to Earth at negative 95 kilometers per hour, so a little bit longer. And we're interested in the velocity of B relative to A. So to help us decide what we're going to do with our vectors, we can use our notation system to say, well, the velocity of B relative to A is going to have to be velocity of B relative to Earth plus the velocity of Earth relative to A, so that these are canceling. The Earth portion is going to cancel away. But the problem is our vector up here is A relative to Earth. So the way we can handle that is by saying that this is equal to the velocity of B relative to Earth plus the negative of velocity that we're given, A relative to Earth. So what that ends up doing for us is that is a vector subtraction. So we're going to take our B relative to Earth, that's this one, velocity of B relative to Earth, and we're going to add the negative of this vector. So that means we're going to flip it, which means its sign changes, and we end up with this vector combination. So that's going to be equal to B relative to Earth is negative 95 kilometers per hour, and that is this one, 95 kilometers per hour in the negative direction, and this is the negative of our positive 85 kilometers per hour. So that's going to be plus a negative 85 kilometers per hour. So that's going to end up with a negative not sure what happened there. Negative 180 kilometers per hour. So, in other words, as the cars are approaching each other, because they're getting closer and closer together, the velocity of A, of car B relative to an observer in car A is going to be a lot faster. For instance, if you can imagine if the car was sitting still, then it would appear that the velocity of is going to be lower, but they're moving toward each other, 180 kilometers per hour. All right, so let's look at another one with two cars. Two cars are traveling east along an interstate. Car A, so velocity of A relative to Earth, is equal to 95 kilometers per hour, and that is to the east. Car B is traveling at 100 kilometers per hour. What is the velocity of A as measured by B? Okay, so we could think of this as we have two cars on, let's say two cars are on the interstate and they're traveling down, we have 2 lanes of traffic, and we've got car A and we've got car B. As car B is tooling along at 100 kilometers per hour, and car A is only going 95 kilometers per hour, car B is going to keep getting farther and farther away compared to car A. If they were at the same starting point here, it's going to be a little bit less. So it's going to look like car B is passing car A, and car A is falling behind. So when we look at this from the standpoint of our vector addition, we're looking for, in the problem, what is the velocity of A relative to B. So this is going to be the velocity of A relative to B equals the velocity of A relative to Earth. I'm setting this up so I've got A first, plus the velocity Earth relative to B. We don't have velocity of Earth relative to B, but we have B relative to Earth. So that means the velocity of A relative to B is equal to velocity of A relative to Earth plus the negative of velocity of B relative to Earth. So if we sketch this vector-wise, we would have 95 kilometers per hour, so we'll call that velocity of A to Earth, and then we'll put B to Earth. B to Earth is going to be a little bit faster, so this is B to Earth. So our vector sum is going to be the sum of A relative to Earth minus B relative to Earth. So I can then flip this vector. And then I can move it tip to tail, A relative to Earth plus the negative of B relative to Earth. And that gives me this leftover zone here, which would be the resultant. And that's going to be equal to A relative to Earth, 95 kilometers per hour, plus a negative 100 kilometers per hour. And that is going to be equal to negative 5 kilometers per hour. So the velocity of A relative to B, is going to be negative 5. So it's going to be the same thing as if car B was sitting still and car A was going backwards at 5 kilometers per hour. Okay, now we've got a ferry crossing a river, and the ferry is headed due north with a speed of 2.5 relative to the water. We say velocity ferry relative to water is equal to 2.5 meters per second, and that is to the north, so that would be a positive. The river's velocity, which would be the velocity of the water relative to the Earth, would be 3 meters per second to the east, so also positive. What will be the boat's velocity relative to the Earth? So velocity of ferry to Earth. Okay, on the floor we'll sketch some vectors here. So we've got the ferry is headed north at 2.5. And then we've got the river headed east at 3. Alright, so We want to add those together, or do we? So let's check our notation system first, make sure we don't have to reverse anything. So velocity of ferry relative to Earth is going to be, start with ferry, velocity of ferry to water. This is velocity of ferry to water. And this is the velocity of water to Earth. So plus velocity of water to Earth. And that means that we are just simply adding these two tip to tail. No reversal of sign necessary. Velocity of water to Earth. So our resultant then is going to be here. So that would be the velocity of ferry relative to Earth. And we can see here from the, once we're sketching this in, we can see that this is a Pythagorean sort of problem. So we've got velocity of ferry relative to Earth then is equal to velocity of ferry to water squared plus velocity of water to Earth squared, and if we want this, we have to have the square root of that. So velocity of ferry to Earth equals the square root of 2.5 meters per second squared plus 3.0 meters per second squared. So the velocity of the ferry to the Earth is going to be 3.91. So we'll just call it 3.9 meters per second. And we need a direction also. So we know that this is 3.9. We know, and that's meters per second. We know that this is 2.5 meters per second, and we know that this is 3 meters per second. So I'm going to go with the theta. I'll go with this angle. Theta is equal to the arctangent of 3 meters per second over 2.5 meters per second. And that's going to give a theta equal to 50.2 degrees. Since we're relative to the north, this is going to be our coordinate axis that we're measuring the angle from. We're at 50.2 degrees east of north. Now, we could also measure it relative to the bank. We found this angle, which theta would have been the arctangent of 2.5 over 3. And we could have had a different angle relative to the bank. So you always need to put what everything's relative to. We need the sense of the vector. All right, next problem. You head downstream on a river in a canoe. You can paddle at 5 kilometers per hour. So let's assume that that's with still water. So the velocity of the canoe relative to the water is 2 kilometers per hour. And how far downstream, well, the river's flowing, so that would be the velocity of the water relative to the bank or to the earth is 2 kilometers per hour. How far downstream are you going to be in 30 minutes? Well, how far you actually go downstream depends on your addition of of vectors. This is actually supposed to be 5 kilometers per hour. Let me change that. Not 2. And I wrote it again. Oh my goodness. 5.0 kilometers per hour. So we're interested in the velocity of the canoe relative to the Earth, and that would, because downstream you would be measuring along the bank. So means velocity of canoe to Earth equals velocity of canoe to water plus the velocity of the water to Earth in our vector addition. These are not at an angle to one another. They're both in the same direction because you're paddling downstream. Water cancels, that gives us canoe to Earth. So that's going to be 5 kilometers per hour plus 2 kilometers per hour. We're going to assume downstream is the positive direction. So that's 7 kilometers per hour. And you've got that in 30 minutes. So we're assuming that the river and the canoe are both constant velocity. So our delta x, our displacement down the river, we'll put the x-axis along the river, is going to equal the velocity of the canoe relative to the Earth times delta t. Velocity of the canoe relative to the Earth is 77.0 kilometers per hour, multiplied by a time in hours of 0.50 hours, which is the 30 minutes. So that's going to be 3.5 kilometers downstream. Next problem. We have another river problem. We have a river flowing due east at 1.5 kilometers per hour. So that's going to be velocity of water, or you can make it river just so you've got some sort of notation that you keep consistent. Water relative to Earth is equal to 1.50 meters per second east. The boat crosses the river from south shore to north shore by maintaining a constant velocity. So velocity of boat to water is going to be 10 meters per second due north. Okay, we have a river, so let's think about our river here. We've got river banks, we've got north, we've got south, we've got our boat on the river that's going to go across the river north to south at 10 meters per second. And we've got velocity of the water, much smaller than that. Velocity equal to 1.50 meters per second. So I'm going to sketch some vectors on this one. We've got our vector of 10 meters per second north to west, and we'll make that a little longer in a moment. And we've got our smaller vector for the current, river current, of 1.5. Increase the size of that a little bit. Alright, so if we're adding these vectors, first of all, we're interested in if the river is 325 kilometers wide, we want to know how far downstream is the boat moved by the time it reaches the north shore. So here's the scenario. We've got a two-dimensional problem. Another problem here, my pen won't start. Okay, so what we have then is the little kinematics problem here, where we're trying to find how far the displacement downstream along the x-axis. But our problem is, and that would be simple enough. We've got 325 meters. We're moving at 1.50 meters per second. So as far as the velocity that we're concerned about, our velocity downstream is going to play a part in how far we move downstream. So it doesn't really matter. The velocity across the river doesn't matter in terms of the velocity for the final solution, but the velocity across the river does matter for something, because to get our velocity downstream, which is going to be water to earth, which is this one, 1.50 meters per second. That velocity is important because it's sweeping the boat downstream. However, if it's just sweeping down the middle of the stream, it's never going to make it across the river. So our time across river is dependent on the velocity of boat to water. Okay? So we have to find how long it takes to get across the river, and then we can use that time. Time is going to be the same in both dimensions, or time applies to both dimensions. We're going to use the time to get how far at the velocity of the water to the earth, how far the boat's going to be swept downstream. Okay, so let's solve first with our, we're assuming that all the velocities are constant, as it says in the problem. So our time, we know that v, average velocity of boat to water, equals delta y, because we're looking at this direction being y, this direction being x. Our change in y, or y displacement, divided by delta t. So our delta t is equal to the delta y over the velocity that's in the y dimension, which is boat to water. Okay? So that's a delta y of, it was 325 meters, divided by a velocity of boat to water of 10 meters per second. So that's going to give us a time interval of, let's say 32.5 seconds to get across the river. So keep that in mind, that even though it's being swept down the river at the same time, the distance, or the displacement on the y-axis is going to be the same no matter what, because, assuming the banks stay parallel to one another, from here to here is going to be 325 meters. If the boat actually sweeps off, it's going to, if we look at a resultant vector, which I'll draw in red, a resultant vector of these is going to go off sort of in this direction. So it's got some x displacement, but its y displacement is still the same as it would have been here. No difference. So from there to there versus from there to there, we're looking at a horizontal displacement that's exactly the same. So 32.5 seconds to move in the y dimension. We then can take our x dimension velocity, which is the the water to earth, velocity of water to earth, times delta t equals the delta x downstream. So that's going to give us velocity of water to earth was 1.50 meters per second times a time of 32.5 seconds, and that's going to be, get my calculator open, 1.5 times 32.5 is 48.75. Downstream. Now let's look at direction also. We know it's downstream, but let's also go ahead and solve for the angle that's there. So we draw in a resultant. We do that in some other color, like maybe light blue. And do that again. Something like this. Now, we know that the orientation of the velocity downstream and the velocity of the boat across the river are at 90 degrees to each other. But let's suppose that we wanted to measure this along the bank of the stream. So let's say that's bank, and this is bank. So we want to measure the angle relative to the bank of the stream, which is actually this angle, which is the same as this angle. So we know that this value is, what is our velocity there? It is 10 meters per second. And our velocity here is 1.5 meters per second. So our theta, which is going to be here, theta then is equal to the arc tangent of 10 over 1.5. So that comes to tangent 81.4 degrees. Is what I'm getting my first run through. 81.5 degrees, and that's from bank. And we also know that this is, the bank is from running in this direction to the east. So this would be north of east from the bank. Okay, so that's going to finish this particular presentation. You should have some classwork that follows, as well as some homework tonight. I will be looking at both of those grades, hopefully have them in, all the grades in by the end of the week. I'll try to keep up with it each day if possible. Good luck with this. If you have any questions or any problems, please email me. And that is the end.